Okay, so this is just going to be kind of a quick little explanation of Le Chatelier's principle as applied to a little bit of a gas equation. And of course, this works for gases and it also works for solutions for things that are aqueous. Le Chatelier's is all about the concentrations of things. So it only applies to gases and to solutions. Of course, because solids and liquids are pure or have a 100% concentration. So if there were a solid or liquid in our equation, we would just ignore that, and maybe I'll show an example of that after this one. But let's start out with a nice easy equation, and this is got some energy associated with it too. Kind of a reposition a little bit here. Okay. So here we've got some endothermic reaction of hydrogen and iodine gases forming hydroiodic acid or hydrogen iodide. And we're going to take a look at if we make some changes to this reaction, how is the reaction going to react or what's going to happen? And all of this comes on based on Le Chatelier's principle, which says that if a system is at equilibrium and we stress that system, that the system will act to relieve that stress. So if we have this equation that's settled in at equilibrium, and let's say we disturb that equilibrium by adding some iodine, what will happen? Okay, so we add some iodine, we close this reaction vessel, and then we see what's going to happen. So this gets a little confusing for students because one of the things that is going to happen is the amount of iodine gas is going to go down. Well, that's because we're talking about right after we added the iodine. So we added some, and then we watch what happens. When we watch what happens, some of that iodine gas reacts to form hydrogen iodine. And so that amount of iodine gas goes down. Because some of that reacts to form more of this hydrogen iodine, it also consumes some hydrogen. So the amount of hydrogen in our reaction vessel would go down. But we ended up forming more of this hydrogen iodide gas, and so the amount of that gas would go up. And that's again just because now there's more molecules of this iodine bouncing around that can get in collisions and become this hydrogen iodide stuff. If we were to add any of these reagents, it would have the same sort of effect. So if I add some H2, well, some of that H2 is going to react, so its amount's going to go down. The I2's amount is also going to go down because it's going to react with the iodine, and it's going to form more of this hydrogen iodine. Now, let's say I added some more of that hydrogen iodine. Now I've got more molecules of that bouncing around, and some fraction of those molecules breaks apart to form this hydrogen and iodine gas. That's the reversible part. That fraction of molecules stays the same. If say 25% of them break down, then that percentage is going to stay the same no matter how many are present. So if I add a whole bunch, well, then more of them are going to break down because 25% of, say, 200 molecules is double as many as 25% of 100 molecules. So if I add hydrogen iodine, after I add it and look at my reaction vessel, I'm going to see some of that breaking down. And I'm going to see, oops, I don't know why I'm putting a plus there. And I'm going to see the amount of hydrogen go up and the amount of iodine go up again because now there's more of these molecules that are able to break down and form these things. So that's what happens if we add a reagent or a product, we shift the equilibrium away from whatever we add. So we end up, if we add something, we end up with less of the things on that side of the arrow and more of the things on the other side of the arrow. We might use this because saying that, let's say that, for example, iodine's pretty expensive and hydrogen gas is pretty cheap. Okay, then we might want to add more hydrogen gas, which is cheap, to make sure we use up all of this iodine or almost all of this iodine, pushing that towards the iodic acid. The same sort of thing happens if we remove. So if I remove any of these items, then the system, if we think about it, if I take away some of this iodine, now there's less of that iodine that could react to become hydrogen iodine. So this forward reaction is going to go a little slower because there's less of it. And yet there still is as much hydrogen iodine as there was, so that backwards reaction is going to keep going at the same rate it was. And the equilibrium is going to shift to produce more of the things that we remove. So if we remove some I2, the system's going to act to make more. If we remove some H2, the system would act to make more. And it will do so at the expense of the hydrogen iodine, because that's what's breaking down to become those other things. Same thing if we removed the hydrogen iodine, the hydrogen and iodine would react to form more of it. And so we'd see the equilibrium shifting to the right. In this case, well, that right-left stuff I should probably explain. So removing iodine, remove some of this. It means that the amount of that then goes up. The system acts to make more of it to replace what we removed. This goes down. And so we say, when we say equilibrium shifts, we're always pointing to the side where we end up with more stuff. So in this example of removing I2, we end up with more stuff to the left of the arrow. So we could say that the equilibrium shifts left. Okay. So that's the real basic idea of Le Chatelier's principle. We can throw a couple other spins into this. So I'm going to say, well, what if I added some heat? Well, you can see that heat is right here in the chemical equation, and it's going to act the same way as adding anything else. If we add some heat, it's going to push away from whatever we add, and we would end up with less of the things on its side of the arrow and more of the things on the other side of the arrow. And then we would say, in this case, the equilibrium shifted right. If we removed heat, it would shift left. It'd pull towards the side of whatever we remove, and we'd end up with more of the things on this side. If we chill this down, if we add heat, we'll end up with more of this. Should make some sense, right? This stuff takes some heat to react to form this. If we add more heat, more of these can react to form more of that. Okay. Okay, one last one really to deal with, and this one can be expressed two different ways, but it's the same thing. And we're going to say add pressure or reduce volume, because those are the same thing, really. If we squeeze the volume, if we've got this in a balloon and we squeeze the balloon, reduce the volume, well, we're going to increase the pressure in that. And again, the opposite of this will be true. So for everything I'm going to say for adding pressure or reducing volume, the same thing would be true in reverse for reducing pressure or adding volume. Okay, and here what we need to do is we need to count the moles of gas on each side. Here we have 1 mole of H2. Here we have 1 mole of I2 gases. So there are 2 moles of gas. Here on this side, we also have 2 moles of gas. Since they're equal on both sides, this will have no effect. If they were unequal on both sides, then there would be an effect. So let's say we have this formation of water stuff going on. And these are all gases. Sorry, I should have put the states. Okay. Some gases combining to form water. Now on this side, we would have 3 moles of gas, 2 of the hydrogen, 1 of the oxygen. And on this side, we only have 2 moles. So here, if we add pressure, you can think about that as being like squeezing these molecules into being the fewest number they can. Because remember, it doesn't, for a gas's volume, it doesn't matter what size the molecule it is, it only matters how many of them there are. So if we want to get kind of less volume of gas, well, we can get less volume of gas by reducing the number of molecules. And so if we add pressure, the system wants to act to relieve that pressure. And one of the ways it can relieve that pressure is by reducing the number of molecules. So if we add pressure, we push to the side with fewer moles of gas. If we remove pressure, then we push to the side with more moles of gas. And so in this case, if we added pressure, we would end up with less H2, we would end up with less O2, and we would end up with more H2O. Okay, so that's, I guess, a real basic run through of Le Chatelier's. If there is anything more you need, please feel free to let me know with any specific kind of topics that might be at issue here, but this should at least get you a good start.